And hello, welcome OpenFoamers. Welcome to this discussion of using an improved mesh to improve this hot sphere in oil case. So in the last video, we talked about some of the meshing techniques, and we saw how much the heat transfer coefficient was improved just by changing the mesh a little bit. Now, of course, I want to bring your attention to this. The fact that when we change this snappy hex mesh dictionary, not only is this level 2, this refinement surface is level 2, and this explicit feature edge refinement is a level 2, and we also added layers as well. So we didn't just add layers, but we increased this refinement to level 2. Whereas in the coarse mesh case, this actually was a level 1 refinement. So you can see in Snappy Hex Mesh Dictionary, refinement surfaces here is level 1, and the refinement at the features is also level 1. So do take note that there is actually some refinement that's being done in this case. So let's take a look at some of the results. So this is the temperature with respect to time. Okay, so we sped up all the way till about 100 seconds. So you can see the time here on this top of the the screen, and we see that this sphere is indeed cooling down. Unfortunately, we do not see any kind of visible plumes that are coming off this sphere that are convecting, and they usually would surface around 100 seconds. And now we are at 200 plus seconds, and still there's no plume being formed for some funny reason. So next thing to do is probably we want to look at some things. Okay. Now we want to look at some things. We want to see whether snappy layer addition case. We want to see the log CHT multi-region foam. Okay, we want to see whether it's that has the what is this? Okay, try again. Log CHT multi-region foam, and we want to see whether has the maximum iterations been exceeded. Okay, so if what am I talking about? We're gonna check for a few things. There's the thing is that there's no plume. Okay, or maybe I'll just start another log here. Clear and clear vi bug log. So observation, first is that the heat flux increases upon mesh refinement, but there is no plume observed. Now if we take a look at ParaView, we see that even at 500 plus seconds, there is still no plume that's forming, and basically the sphere in the center remains like at 370 degrees, 350 degrees Kelvin. So this is very, very strange. Why is there no convection? Okay, so no convection observed in this regard. Okay, and if we were to take a look at the U, okay, I use a slice plot. Let me change to U. I mean, yes, you will see a little bit of this what do you call that? This U magnitude is non-zero, meaning to say the fluid is moving, but it's moving way slower than what we would have expected previously. So the last in those previous videos, we saw that they were on the U magnitude was on the order of 10 to the minus 3, not 10 to the minus 4. So it's actually about 10 times slower, this plume. Okay, so let's make another observation. Velocity profile around sphere shows non-zero convection is happening, or non-zero velocity convection is happening, but it is about 10 times slower. For a higher heat flux, you have lower convection, which is again a very strange phenomena. So let's take a look at this to see whether, you know, is it due to the iterations reaching a max iteration. So what do I mean? So you have your domain here, your sphere in your box. Okay, so I will have iterations for velocity, temperature, etc. So do these iterations reach okay, let me type that out, it's easier. Do they reach convergence, or do they just max out before convergence? So what do I mean if they max out before convergence? It means that the U fields, the velocity fields and temperature fields are not solved, and the solver just exits without resolving the field completely. So does that happen? In this case, it does not look like it does happen. So the initial residual is a lot, but the final residual is like, you know, 10 to the minus 6. And the number of iterations, it's about what do you call that? It's about 11 iterations, which is less than 1000. So this doesn't seem to be the problem at all. Okay. So in fact, we can of course shift the Courant number a little bit more. Okay. You see that the diffusion number and Courant number are changed significantly. So yeah, so what do I mean by this? Okay, I'm having this intuition now. So let me draw for you what I'm feeling. Okay, so you have your mesh here. Right, you have your mesh here, and you also have let's say you have a heated surface here. So there's a Q that's going in, there's heat that's going in. So now you have this kind of a setup, and then you realize, okay, maybe the first cell will get heated up. Alright, first cell get heated up, and the second set of cells also get heated up. And these cells at the second site tend to rise, because ones over here will get stuck, undoubtedly. The cells over here will get stuck, and these, usually the second cell onwards, they will have more velocity, because these ones are like closest to the no slip condition. So the velocity profile will usually be like that for convection. If you have a velocity versus distance from the surface kind of a graph, there will be a peak velocity somewhere here. Okay, so that's the usual convection boundary layer kind of a structure. So if if your mesh is very fine, there may be lots of so-called continuity problems. Maybe they try to resolve it numerically. It means the velocity here is 0, and sometimes a small positive velocity going up may not maybe a little too slow to get this velocity going. Okay, so in other words, I'm saying there's a lot of inertia, and maybe the size of the mesh actually contributes to some of this inertia. So that's a guess. It may not be right, but if this thing was bigger, there will be so-called less cells to calculate, and what I mean is that, okay, if this is 0, this is 0, this is 0, and there's some positive velocity coming here, so when they iterate, they have to consider these 3 cells which are 0 over there. If there are so many cells with 0 velocity in them, then maybe it takes a while more for the whole velocity field to adjust to something that's non-zero. Now that's just a feel I have. Yeah, not completely accurate, but it's a guess. Maybe the Couron's number, when it's too low, you don't allow it to be high enough, then you may have this the cells getting a velocity stuck. But that's just a thought process. It may not be right. Oopsie. Here. All right. So that's the other thing, and of course, one pretty obvious thing is that if we take a look at wireframe or surface with edges. Okay, so this shows you where the velocity is. For some reason, the velocity here is not like convecting upwards. Yeah, this is not convecting upwards, perhaps due to the earlier aforementioned reason. So we can try and increase the time step and increase the maximum diffusion number. This is some of the possible sources of error. Maybe we need a thinner boundary layer, finer mesh over here to help resolve that boundary layer. I'm not really sure. So there are a number of things we can do, and one more possible source of error. Okay, possible source of errors. The mesh is not fine enough. Courant number too small. Time step too small. Yeah. What else? Okay, there was one more. FE scheme in the solid directory was changed. What? Okay, let me highlight that one for you. What do I mean by that? If you go to System Sphere FV scheme, okay, we'll notice that because we are debugging in the past, we use a Crank-Nicholson and cell multi-directional limited Gauss linear scheme. Now, perhaps this reason might have caused some calculation to go wrong. Yeah, and if we take a look at the how wrong did it go, we can take a look at the post-processing average heat transfer coefficient, and we take a look here. Now, the heat transfer coefficient, it ranges from very high at minus 165 at like 2 seconds. However, it rapidly drops to almost 0, where you see it's a 0.98 at about 546 seconds. And you look at the temperature, it remains at 353 Kelvin for pretty much the whole simulation. There's practically no heat loss after the next 500 seconds because there's no like convection happening. So again, this is all very, very weird. I don't really know what's happening. Okay, so Maybe something to do with the sphere FV schemes was part of the reason why. And of course, there is a what do you call it? There is a problem. This is still like results nonetheless. We can copy some of the data over. Okay. So data for subsequent tests. Okay, so first this test is like test okay, how shall we name it? We can name it, okay, it's not responding now. We can name it the refined mesh case with layer addition. No plume observed. So for that some reason the thing is kind of stuck. So let's look at Notepad and let's get our data out. Okay, let's go. Go to OpenFoam here. And I'll go to processing, oil. I'll just use the average heat transfer coefficient here, because there is no need to keep guessing using the wall heat flux. We already found that this is actually pretty representative of the heat transfer coefficient of the whole sphere, and this is averaged. So there's no need to go through the whole process of summing up over all areas and then looking at the wall heat flux and dividing by the area of the sphere. So this actually is good enough. So let's open with Notepad. More apps. Okay. Alright, so I'm gonna get all of this and I'm gonna paste it in an Excel. Very simple. So it pastes nicely. Alright. So this is the set of data from this. And so the next experiment for this, I'm going to do a very simple all clean. Alright, I'm going to wipe out all this data because I don't really need it. It's kind of junk at this point, but we know what we did. We actually refined the mesh to level 2, and we also did some layer addition. So let's we can get some things out one error at a time. Okay, we can do one error at a time. So first thing first, the easiest one to change is this FV schemes in the solid directory. Okay, so to change that, I want to just take a look at the coarse mesh sphere oil system sphere. Okay, I want to look at the FV schemes here and just take a look at what they are. First thing first, Euler, Gauss linear, corrected, linear, and corrected. So I can actually just copy and paste all of this, and I want to paste it into the snappy layer experimental case. Okay, so this is a quick debug. It's not quite working right yet. Okay. GitHub, OpenFoam Heat Transfer, CHT multi-region foam, and what is that? Oh, snappy layer. Additional case, experimental case. Go to System, Sphere, FV scheme, and here you are. So I'm just gonna delete all of this and then replace it with replace it with this. Undo, press insert, paste. So I think the Crank-Nicholson scheme I can kind of keep. I don't see that changing anything too much, but okay, never mind. For consistency's sake, I'll just delete this. Because you're debugging, so you don't introduce new variables into the situation. So we have a Gauss linear corrected, Gauss linear, linear and corrected scheme. We can do this. We go to system. One more thing. We can go to system. Go to system. Control dictionary. And I want to change the purge right to 6 because I do not want all of this data. But what a purge right that's equals to 6 will mean is that okay, let's say I have 5, 10, 15. So these are the time steps: 20, 25, 30, 35, 40. So let's say at 40 seconds, t equals 40 seconds. You don't want to keep. You only want to keep the last 6 time steps. Then you use the purge right equals 6 to mean that I will only keep the latest 6 time steps. Everything else I will just delete. So that's what purge right does. However, the nice thing about that is that purge right does not get rid of. It doesn't get rid of what do you call that? Yeah, it doesn't get rid of our post-processing data, which is what we need for heat flux. And also, if we take a look at the latest time steps, we should be able to see the plume forming. We should be able to see the plume as it develops. So that's very useful. We can see the presence of a plume forming. If let's say we can see the presence of a plume forming, in other words. Okay, so that's all. We can at the later steps. So that can tell us, that can indicate to us that our simulation is going right, and we do not need to keep so much data inside. So that's one of the ways we can do it. We end at 100 seconds because that's usually when the plume starts to form. Okay, so you can save and quit, and let's do a run. All run serial end. Okay, so the case is 32273. So it's running in the background. 32273. Okay, PS and A. I mean, I can use a kill process to kill it, but I don't want to do that now. So we'll have this going on. So I'm changing the FV schemes in the solid directory. Hopefully that that gives us some semblance of improvement, so that it eliminates a variable, so it makes debugging easier. So when debugging, we want to eliminate as many variables as possible. Okay, so the FV schemes is one of them. Anyway, the Courant number, diffusion number is 10. The Courant number is I think over here. It means the velocity is very small, which means the thing is pretty stable. Okay, so it's at about 30 seconds now, and I can do a touch. The sphere foam is there, so I can delete this. And delete the slice filter first. delete this sphere, delete the slice, and delete the sphere. Okay, I will go to snappy layer add experimental case. Okay, so this is where it is. You can go to wireframe. We add a slice filter. Data analysis, common slice. Add the slice filter. Oopsie. Reset. Okay. Instead of P, it goes for a U, a T. So let's see if there is any plume forming. Okay, reload. Alright, and then we can take a look at the it's at 54 seconds now. We can take a look at the post-processing. Average heat transfer coefficient. And here we are. Again, it starts about 1.65 and about 58 seconds it's about 120. Okay, let's see whether at the 58 seconds it's the same amount. So we can see whether it's changing significantly. So yeah, at 58 seconds heat transfer coefficient is about 120, which doesn't it means that changing the FV schemes of the solid doesn't really change much of the it doesn't change much of the solution. So here is one. Changing FV schemes doesn't change much of the solution. Next thing is that we note the Courant's number or the diffusion number. Vi log.cht. Oops. Remove log.cht. I made that by accident. Vi log.cht multi-region form. Yeah. You look at the diffusion number. We normally have this set at 10, so that's the limiting factor. So Courant number being too small is not a factor because okay, my thought process was this. I actually, during the debugging process, I reduced this max diffusion number to 0.99, which is just below 1, and I thought that that itself would affect the Courant's number, since diffusion number is kind of the limiting thing here. Setting the diffusion number to be even lower may make the Courant number lower, but that was not the case. So the Courant number being too small and time step being too small is not the case. Diffusion number set at 10, not 0.99. Okay. So that the only next possible step is to increase the fineness of the mesh. Okay, so increasing the fineness of the mesh and doing proper layer addition will be the next step to getting this thing working correctly. Hopefully that sets up the convection plume we are looking for. Otherwise, we'll just keep continuing debugging until we find out why this is happening. So thanks for watching. I'll see you guys again. Bye bye.